All right, in this video, I'm going to be just reviewing some of the concepts from 4.3 and 4.4. So this is a review of 4.3 and 4.4. So that's this is the addition method, 4.3, solving systems using addition. And 4.4 is the one dealing with the word problems or the applications. So you have to set up systems and then solve them, okay? All right, so if you get a problem like this one, so for my first example, you might have a problem that involves two equations. These are in what we call standard form. The x and the y are on the same side. All right, so when I have something like that, you're probably like me, the best way to do it would be to use the addition method. And what my goal is to get the number in front of either the x or the y to be opposite of what is in the other equation. So looking at this one, oops, I don't want an arrow on it. Let me get it to be just a line. Okay. So to get the number in front of the x and the y to be the same, just opposites of one another. So really they're almost the same right now. We've got 6x and 6x. If I multiplied one of the equations by -1, I'd get a -6x. But you have to distribute that -1, multiply all the way through on both sides. Now I'm just bringing that top equation over because I like to keep my systems lined up like this. All right, now I'm ready. I've got it ready to where I can add, and these cancel out. They would wind up being 0, and then +7 and -9 would be -2y, and +4 and -12 added up would be -8. Now when I divide by -2 on both sides, I wind up with y equaling negative divided by negative is positive, and 8 divided by 2 is 4. Right now, I know what I'm looking for is the ordered pair that satisfies these. You know, we don't graph these, but in the back of our mind, we're thinking that we're looking for that, and we need the ordered pair, and all we found so far is the y coordinate. So what we're going to do is go back to one of these equations. I'm just going to use the bottom one. These, it looks like it doesn't matter that much which one I use. I'm going to use the bottom equation and put it right there where you see the y. That's in place of the y, you're putting the 4. The y is not there anymore. So you have 6x plus 36 now is equal to 12. So you're going to solve that equation. So that's one where I'm going to come in and I'm going to subtract 36. Gives me a negative 24 on the right. Oops, I want that in black. I want it to be pretty when I'm finished. So that's negative 24 on the right, positive 6x on the left. Then I need to go in and divide by 6 everywhere. So that's going to give me x equals -4. Okay, so what I'm thinking I've got, what I believe the solution to be is the ordered pair -4, -4. Now on ALEKS, they'll just ask you for x equals and then y equals, but really you're looking for that ordered pair. Now, I used the second equation right here when I went and tried to find what the x value was that corresponded to the y of 4. So here's the way to check it. Do this on a quiz. Go in and plug in what you got for your x and your y. Plug in the -4 for x and the 4 for y and see whether it equals 4 when you're finished. And 4 does equal 4. That means I know for a fact this is correct. Okay. All right, so let's try another one. So what if we got this problem? This one's going to be a little bit harder. What if we are asked to solve the system? So they're asking us to solve again. And this time we have equations that have the x and the y on the same side. So that makes it a good candidate for the addition method. But this time, I'm going to have to do something to both equations in order to get the same number out in front of these variables with one positive and one negative. You know, I want them to be opposites. So what I do is I look at how 2 and 5 are out there and how a common multiple of 2 and 5 would be 10. So if I multiply the top by 5 everywhere, and the bottom equation by -2, not -2, 2 everywhere, and then I check it and see how this would be 10, this would be -10x, that would be positive 10x. See how the negative was already part of the 2? So that gave me the negative on the 10. And then down here, when I multiplied by positive 2, I got a positive 10. I always check that with my plan, with what I'm planning to do, that that's going to happen, that these are going to be opposites before I do any more. Okay, so that's going to work. Now I'm just going to distribute that 5 all the way through on both sides. So I'm going to have negative 10x plus positive 15y equals positive, that's 70, isn't it? Okay. All right, on the bottom equation, it's going to become 10x plus positive 4y equals positive 6. So I made it where the x's canceled. I could have just as easily had the y's cancel, but I made the x's cancel, and I wound up with 19y equals 76. Let's see. I got to divide by 19. And when I do, I wind up with y being 4. Okay, good. All right, now I need to find the x. So think of those original 2 equations are like a formula telling you the relationship between the x and the y. So right there where the y is, right here, I'm going to put 4. And I'm going to use that formula, putting 4 in place of the y, to work that out and find out what x is. So that'll be 5x plus 8 is 3. And I'm going to now be solving for x. So I'm subtracting 8 from both sides. That gives me 5x, the 8's gone, equals -5. And when I divide by 5, I wind up with x equaling -1. So my ordered pair is -1, 4. All right, now I'm pretty sure I'm right, but I can check it. And I'm going to do that by taking that -1 and I'm taking the first equation. Let me write it down for you. The first equation is the one I didn't use to find the x. I used the second equation. So the equation I didn't use, I'm going to write it down. And then in place of x, I'm going to put a -1. In place of y, I'm going to put a positive 4. And when I'm finished, I'm wanting to see, does it turn out to be 14? So sure does. That's 2 plus 12 does equal 14. That means I know this is right. I'm ready to type in my answer. Okay. So the first problem we didn't have to do, we only had to adjust one of the equations, right? We already had the 6x here. So all we needed to do is multiply through by -1 on one of the equations. Okay. With the second problem, okay, I had to adjust both equations in order to create opposites so that when I added, those would cancel out. Okay. All right, so now let's look at those special cases. You've seen this in homework. All right, so, sometimes you get a situation like this. Where you try to cancel out one of the variables or get things ready to cancel out one of the variables, like I might be focused on getting rid of the x, okay. And when I do, not only does the x go away, but the y goes away, and I have just 0, no variable at all left, equal to 16, okay. Or something kind of similar to that might be like this one, where I'm focused on maybe getting rid of one of the variables. Let me choose the x. Okay, so I'm planning on making the x's cancel. They're already opposites. That's like a 1 and a -1, so I can add them and they're gone. But then the y's cancel out too, and I get a 0 equals something. This time 0 equals 0. Okay. Whenever you get that situation where you lose your variables, both of them, You're trying to eliminate one of them, but when you eliminate both of them, where you get a statement that's the resulting statement is just false or a statement that's always true, that's an indicator that you have a special case. Okay? So if you get the false situation, that indicates that your lines, that there's no point of intersection. So there's no solution, no point of intersection. See, these lines must have been parallel, okay? Never intersecting. So when you get a false equation that doesn't have an x or a y, it's just zero, some number equals some other number, something that's not true, that's telling you that the system doesn't have a solution. Okay? Now, when you get a case like this, where you have something that's always true, still a special case, it's this situation. You wind up having infinitely many solutions, infinitely many solutions. Okay? It's really all points on the line would work. You've really got, here we had parallel lines. Here what you have are coinciding lines. They're really the same. So the solutions would be all the points on that line because all the points are in common. Okay, so neither of these is the usual case. The usual case is that one, and you're looking for the single ordered pair. So anytime both variables are eliminated, that's a indicator that you must be having one of those special cases, and then your job is to get straight which one it is. So this second one that I had wound up having infinitely many solutions. The solutions would be all the points on the line. And so if it asks you for the equation, I noticed on one problem, they asked you to say the solutions must satisfy the equation. They wrote it like this. The solutions must satisfy the following equation. So they're saying that, not all ordered pairs anywhere would work. This one does not. The only ordered pairs that work are the ones that are on that line. So the ordered pairs must satisfy a certain equation. Okay, what I think is the hardest part of this one is they want the equation, they have y equals, and then you're supposed to put your answer there. But see, these equations were not in the y equals form. So what you should do is take one of them. I'm picking this one, negative 1x, or it was negative x plus 3y equals 9. I'm going to take that equation, I'm going to rearrange it to get the y by itself, and then I'll be able to fill in that spot. So basically, the solutions must satisfy this equation right here, but they just want it in the form y equals. So that means I need to rearrange a little bit. So I'm going to add x to both sides to get 3y equals x plus 9. So we're just getting the slope-intercept form of this equation. Then I'm going to divide through by 3. Go ahead and distribute that into everything. And you wind up with y equaling, you can write it x over 3, or you can write it 1/3 x, and then 9 over 3 simplifies to be 3. So you just go on and take that equation and get it in mx plus b form. That right there, I'm afraid, is going to be the part that you miss more than anything else. You might know that it's infinitely many solutions, but you may not understand how to get that equation. Okay? All right, and then I'd like to do a couple word problems with you. So let's take a look at a word problem like this. Okay. All right, so we have a fruit company. I'm just going to write it, and you can be thinking about it as I write it. A fruit company delivers fruit in 2 types of boxes. Okay. Large and small. Large It's supposed to just be a colon right there. Okay. A delivery of, and then it goes on to say 3 large boxes and 5 small boxes has a weight of 75 kilograms. Okay. Then it goes on to say a delivery of 9 large boxes and 7 small ones has a weight of 171. Kilograms. Now let me check my numbers. Yep. And then the question they're wanting us to answer is how much does each type of box weigh? Okay. All right, so just kind of read through that. Remember, you scan it as you read through it to get the sense of what they're asking you for. But your focus is actually going to be down here at the question first. That determines what you're going to let your variables stand for. Okay, so let me set it up then. So I'm going to let X be the weight of one large box, and I'll let Y be the weight of one small box, because there's only those 2 types. All right, let me squeeze that just a little bit more. All right, in fact, it might make sense for you to see it kind of over to the right here. So it's like X is the weight of a large box, and Y is the weight of the small one. Okay, so let me just do it over to the right, and then we'll do the solving below. All right, then you see this sentence right here, a delivery of 3 large boxes. So if I have 3 large boxes that weigh X kilograms each, 3X would be the weight of those large boxes. I've got 5 small boxes, they weigh Y kilograms each, so 5 times Y is the weight of the small boxes, and altogether it's supposed to weigh 75. Then this sentence says a delivery of 9 large boxes that weigh X per box. So that's the weight right there. That's the weight of all 9 of the boxes. And then I've got the weight of all the small boxes, and that's supposed to equal a total of 171 kilograms. Okay. So do you see how it then looks like those equations we were dealing with on the previous page? So now I'm going to wind up, previous couple of problems, now I'm going to wind up trying to solve this. So I'm kind of thinking I'll adjust the X so they're opposites. Because see how that's a 9 on the bottom? I can multiply by -3 all the way through on top. Okay. All right, so I'm going to move to the right because I like to distribute that way. So that would be -9x minus 15y equals, darn it, 75 and 75 would be 150. So another 75, 150, wouldn't that be 225? It'd be -225. Bottom equation, I'm not doing anything to it. I'm just writing it so it's lined up with the rest of this. And I wind up with -8y equaling a 4, 5. Ooh. I'm surprised because I don't think that turns out right. So 5 minus 1 is 4. 7 from 12 would be 5. And that would be negative. I was hoping it was going to turn out to be nice. I'm checking my numbers. I think all the numbers are correct. So maybe you just round off or something a little bit. I don't know. All right, so I'm going to divide by the negative 8 on both sides. Because that is negative 15 and 7 would be negative 8. Okay. And I wind up with y equaling, but 7 would be 56. So it's like 6 something. So it's 6 point. And grab a calculator real quick. 54 divided by 8. Keep entering it wrong. 54 divided by 8 turns out to be 6.75. So that didn't keep going forever. So I'm just going to leave it at 6.75. Now, when you get something that's a decimal, if you wanted to, you could go back and eliminate the other variable. But I'm going to go ahead and just take that right there, which is the y, right? It's a y. So I'm going to plug it in for the y in one of the equations. You could use either equation. Actually, I think the top one has smaller numbers, so maybe it would be better for me to use the top equation. So I'm going to take 3x plus 5y equals 75. Then right there where the y is, I know my y is 6.75. So I'm going to put in a 6.75 for the y. And then my equation just has x's left. So 6.75 times 5 is 33.75. Okay, so now I'm going to subtract the 33.75 from both sides. Which gives me 3x equaling 41.25. And then when I divide by 3, I get that x equals 13.75. All right, so one large box weighs, that was our x, right? So you go back and you kind of check. X was a large box. So one large box weighs 13.75 kilograms. One small box weighs 6.75 kilograms. That was our y. So remember, this was your x, this was your y. And on the on Alex, they typically just will have a spot that says large box. Oh, let me see how they word it. They'll say weight of each large box, and then they'll say weight of each small box. So you just make sure you put those into the correct spots. Okay. All right, let's try one more word problem, slightly different type. Okay. Let's do one of those that involves distance equals rate times time. So a boat, I'm going to summarize it without writing it all out. It says a motorboat takes 3 hours to travel 108 miles going upstream. Boat takes 3 hours to go 108 miles upstream is the first sentence. I just kind of abbreviated a little bit. It said a motorboat takes that. Okay. The return trip takes 2 hours going downstream. Okay. Then it says, what is the rate? Rate of the boat. It's an O. In still water. And what is the rate of the current? Okay. And it's that last sentence that kind of tells you what to let your variables stand for. So the rate of the boat in still water and the rate of the current is what we're going to let our X and our Y represent. So I kind of showed it like this. Rate times time, we know equals distance. Okay. We have the downstream situation. We have the upstream. You don't want to put X and Y in there for the downstream and the upstream. You want to think a little bit. Okay. You want to think a little bit about it. You want to think about it this way. We're going to let X be the rate in still water. Wish I had left a little room right here, but I'll squeeze it in. X is the rate of boat in still water. And then Y is the rate of the current. All right. Then if you're going downstream, that means the current is helping you so that you go faster. So it's X plus Y. If you're going upstream, that means you're going against the current. That means the current is working against you. So it'd be X minus Y. Now it tells you that the boat took 3 hours when it was going downstream. And then in another sentence, it says the return trip took 2 hours going, oops, have it backwards, sorry. The boat takes 3 hours going upstream. So that's this one. And 2 hours going downstream, because you can go faster when the current is helping you. Okay. And that 108 miles is actually going to be the distance for both of them, but put it over here to the right a little bit. You know, they're going down upstream and then turning around and going that same distance back to the starting trip. A return trip is the same length. But the thing that we're going to do is take advantage of rate times time giving us distance. So we know 2 times the X plus Y would have to equal 108, and 3 times the X minus Y would equal the same thing, 108. So there's actually your system. All that other stuff was just working on getting it set up. Now, usually when we have parentheses, we're used to just distributing. I'm not multiplying the 108 by 2, though. You see, the equation just has me with parentheses there. So I'm not doing any of that, like trying to tweak the equations yet. I'm just distributing the 2 to get rid of only that should have been a 3. The second equation should have been 3 times X minus Y. Okay, now I'm going to distribute the 3, get 3X minus 3Y equals 108. And we've got everything set up, ready to go. And now this looks like those systems we were working on earlier. All right, so I'm noticing that the Y's already have the negative in front of one of them. So I think I'm going to focus on getting rid of those. I'm going to do 3 times the first one so that this spot, when I finally distribute to there, would be 6Y. 2 times the bottom one. Okay, and I'll do 3 on both sides. 2 on both sides here. All right, when I do the 2, do you see how that would become negative 6Y? I always check that it's going to work out to get me opposites. All right, so now I'm going to go ahead and do the 3 everywhere. So it'd be 6X plus 6Y equals 324 would be the top equation. The bottom one would be 6x minus 6y equals 216. Okay. All right. I'm adding these two equations because these are opposites, so they're going to add up to be 0, but the 6x and the other 6x are both positive. Do not cancel those out. They're both positive. That would be 12x equals, and this would be 530, 540. Okay. So now I know I just need to divide by 12, and that'll give me my x. So my x turns out to be, let's see, 12 goes in there, 4. Let me just do it on my calculator real quick. 540 divided by 12. 540 divided by 12 would be 45. Okay. I need to find the other coordinate. So I'm just going to take the top equation, 2x plus 2y. I go ahead and I like it where it's already distributed. And so right there where x is, I know x is 45. So right there where x is, I'm going to put a 45. So I'm going to just work it out. This is kind of slow. I hope the video turns out okay. So I wind up with 90 plus 2y equaling 108. I'm going to subtract the 90 from both sides because now I'm focused on getting the y by itself. So I get 2y equals 18. Divide by 2. And I wind up with y equaling 9. All right, so let's think about those to interpret them. So we're going to go back up. X was the rate of the boat in still water, right? See it? So X was the boat in still water. Y right here was the rate of the current. Okay, and let's see, it was hours and miles, so miles per hour. So our interpretation would be the boat, I'll just say the rate of the boat. The rate of the boat, in still water, so that's like if it were on a lake, is 45 miles per hour, and the rate of the current is 9 miles per hour. Okay. All right, so just wanted to do a couple more problems from 4.3, a couple more from 4.4, because you're going to wind up having a quiz on 4.3 and 4.4 on right the first day when we get back from Thanksgiving.